So in the last section, we were looking at how we could calculate the pH for a buffer using the Henderson-Hasselbalch equation. Now remember, when we were looking at that equation, we said that the pH equals the pKa, or the negative log of the Ka, times the concentration of your base over the concentration of your acid. So if we change this ratio a lot, we're going to have big changes in our pH. Our buffer can only moderate small changes. We don't want to have big changes, okay? So we want to add little amounts of strong acids or little amounts of strong bases, but if we add too much, then we're going to see large changes in our pH, okay? Now, our best buffers are going to be when our HA, or our acid, is equal to our base. Now, the reason is, when we looked at that last equation, okay, when we have the concentration of our base the same as our concentration of our acid, those are going to be canceling each other out to form a 1. The log of 1 is 0. So when we have a buffer where the concentration of the acid is equal to the concentration of our base, the pH is going to be equal to the pKa, or the negative log of that Ka value. Now, the reason that this is important is this will allow us to choose proper buffers for different reactions, okay? So here I've got several different acids that I can use to make a buffer. I can use one of these acids and their conjugate base, but I want to choose it so that I have a system where the buffer is at about a pH of a 4.3. So here's how I can use that little fact. I said that if the concentration of my acid is equal to the concentration of my base, then the pH is equal to the negative log of the Ka. So here's my acid. So the pH is equal to the negative log of 1.35 times 10 to the negative third. If I plug that into my calculator, I get the pH is 2.87. Not going to be a great buffer system for a 4.3 pH. Okay, let's look at propanoic acid. The negative log of 1.3 times 10 to the negative fifth. I get a pH of 4.88. It's closer. Still not great though. If I take benzoic acid and plug that in, I get a pH of 4.19. And if I take hypochlorous acid and plug that in, I get a pH of 7.46. Now, of the 4 values I've got, 4.2 is going to be the closest to 4.3. Now, it's still not exactly 4.3, so I know that in my system, I can't have equal concentrations of my acids and my base. So I would need to figure out the log of my base over my acid would need to be 0.1, and then that would tell me what ratio I needed to plug things in. Easy enough. So that's how we figure out how we set up our buffers, is we actually look at the Kas and use the Kas to determine the pH value. Okay? So 15.4 talks about titrations, and we've talked about titrations before, but it's been a while. So as a quick reminder, what a titration is used to do is I'm finding the concentration of an unknown solution. My unknown is going to go in the flask at the bottom. Okay? Now I know what it is, I just don't know its concentration. Okay? The thing that I don't know the concentration of, I'm going to call the analyte. Now I'm going to take something I do know the concentration of, and I'm going to put it in the burette. I call this the titrant. Now in this case, I have an unknown acid concentration, so I'm going to neutralize it with a known base concentration. Okay? Now, because all of my acids are going to be clear and colorless in solution, and all of my bases are going to be clear and colorless in solution, I'm going to have to add something called an indicator that's going to tell me when the reaction is done. My indicator is going to change colors, and when it changes colors, we call that the end point, because that's when I'm going to stop my titration. Okay? So I can use an indicator. Another method I can use in my titration is I can actually stick a pH meter down here, and I can monitor the pH. Now, because I'm starting with an acid, my pH is going to start low. As I'm adding more base, more base, more base, the pH is going to start to rise. Halfway up this peak, I hit something called the equivalence point. At the equivalence point, the concentration of my acid is equal to the concentration of my base. They are equivalent. Now, if you notice, this levels out up top because eventually I'm going to hit a point where all of my acid is used up. The only thing left over is base. Okay? So I can use either of these systems. Now, if I'm looking at a strong acid and a strong base, remember, a strong acid is going to dissociate completely, so I have only H+. A strong base is going to dissociate completely, so I'm only going to have OH-. When my H+ and my OH interact, they form H2O. It does not go both ways, so the pH is going to be 7 at the equivalent point. So if I look at this curve, I know that this curve is for a strong acid, strong base, because my equivalence point is at 7. Okay? Now, just a quick reminder, here's how we solve titration problems. So I've got 50 milliliters of HCl down in this flask. I don't know the concentration, but I do have 1.3 molar NaOH up in this burette. So I'm going to start adding NaOH through the burette. At 22.8 milliliters added, my reaction is going to change colors. I reached my endpoint. So I want to find out the concentration of HCl. So here's what I do. I start with the one I know most about. So I had 22.8 milliliters of NaOH. I know that I have 1.3 moles of NaOH for every 1,000 milliliters of NaOH. Remember, my molarity is moles per liter or moles per 1,000 milliliter. So I want to get rid of moles of NaOH. Instead, I want moles of HCl. Now, when I change from moles of one element or compound to another, I use the mole ratio from the equation. 1 HCl is going to neutralize 1 NaOH. It's a 1-to-1 molar ratio. So I've got 0.0296 moles of HCl in my container. But that's not molarity. That's just my moles. Molarity is moles per liter. So I've got 0.0296 moles of HCl. I've got 50 milliliters, or 0.050 liters. So my molarity is 0.592 molar HCl. Okay, so I always start with the one I know the most about. Now, if I have a strong acid, strong base, my equivalence point is going to be 7. If I have a weak acid and a strong base, my equivalence point is going to be greater than 7. The reason is, here I've got my weak acid. My weak acid reacts with my strong base to form water. That doesn't affect the pH. But here I've got this F minus. F minus is the conjugate base of HF. So I've got this F minus floating around in solution. So what it's going to do is it's going to react with the H2O. It's going to form HF, and it's also going to form OH minus. So my solution is going to be slightly basic when all of this is used up. Okay? So if I look, that's not right. If I look at the curve, there we go, what I'll notice is that my equivalence point for a weak acid is going to be higher than 7. Okay? Something to be aware of. Not all of my curves will have the same shape. If we look, the stronger the acid, the lower my initial pH, so it's going to have a much steeper curve up. The weaker my acid, the higher it starts, and so the much shallower curve I'm going to have as it goes up towards that equivalence point. Okay? So if I'm starting with a weak acid, it's going to be higher, and the equivalence point is going to be above 7. The stronger it is, it's going to be lower. Okay? Something to be aware of.